Welcome to the second video in the object-oriented programming lectures, where in the previous lecture we described what objects are. We learned about attributes and methods, attributes being the variables that are bound to an object or that belong to an object, methods being the functions that are bound to an object. And we learned that attributes are essentially the properties of an object. They describe its state. These might be things like, if we're considering people, your hair color, your age, your name. And then we also discussed methods, things that an object can do. So this might be like riding a bike, or driving a car, or performing addition or subtraction. Things that hopefully you are all able to do. Although living in New York, I know quite a few people who cannot drive a car, and that's perfectly fine. So, where does an object get its attributes and methods from? Where is it defined what these things should be? Because, for example, a name and hair color and age might be very good attributes for a person, but they're not very good attributes for, say, a chair. A chair probably doesn't have a name. It has an age, it has that in common with people, but it doesn't have hair color, for instance. So, chair and people are two very different types of objects. They belong to different classes of objects. And a class is a blueprint for how an object should behave, what it should be like. As I mentioned, all people share certain properties in common, and those properties are described by our species, our class of organism. Let's consider some examples of classes in Python. So, classes are where we define objects and how they work. And this goes beyond just the methods and attributes of an object. For example, we could look at the methods and attributes of a dictionary, but that tells us nothing about how the elements of a dictionary are stored in memory. The details of how the dictionary is constructed are contained within the class definition. We will, in the remainder of the notebook, define some of our own classes to get a better understanding of how objects that we interact with are defined and how they might work. And in Unit 2, if you progress to the Machine Learning Unit, Unit 2, in this data science series, you'll probably be doing a lot of your own class definitions for various machine learning models. So, and just having an idea of how classes work is going to help us better understand more complex objects like plot-making objects, objects that represent tables of data, or classes for doing statistics and regression. So our example is going to be a class for working with fractions called rationals. So fractions are in mathematics called rational numbers, and we're going to write a rational class to represent such numbers. And thinking about rational numbers or fractions, we know that they have essentially two parts, a numerator and a denominator. So those are going to be the class's attributes, or the object's attributes, the numerator and the denominator. And also, when we work with them, they have a particular representation. We represent them as the numerator divided by the denominator. This sets them apart from, say, decimal numbers, which are represented as digits, dot, more digits. Or in some parts of the world, digits, comma, more digits. Fractions we represent as numerator divided by denominator. So we're going to define a very small, simple, rational class that defines the numerator and denominator attributes and is capable of creating this representation of a fractional number of numerator divided by denominator. To do these two things, we're going to define some special methods called init for initialization and repr for representation. So init tells Python how to create or initialize or instantiate an object of this class. Repr tells Python how to print out a representation of that object. Let's begin with init. Well, let's actually begin with the syntax for defining a class. And that syntax is somewhat similar to the syntax we saw for defining functions. When we want to define a class, we start with the class keyword. Then we have the name of the class. Unlike functions, this name is usually capitalized and written in camel case. So for example, if I wanted to define a object that would perform linear regression, I might define a linear regression class. And I would write it this way with camel case and with the first letter capitalized. Most other names in Python, for example, if I was writing a function to do linear regression, I would write it this way. So neither of these things are going to do anything, but I'm just showing the naming conventions. So functions will usually be lowercase with different words separated by underscores. That's true of variables as well. Variable names are usually lowercase separated by underscores. Class names are usually written in camel case with the first letter capitalized. So that's what we see with this rational class. Our class is going to inherit from object. Now, strictly speaking, you don't need to put object here. I'll explain inheritance later on. In Python 2, it was necessary to include this. In Python 3, by default, this is essentially always assumed to be there. But since I've been working with Python for a while, and I've done a lot of work in Python 2, I'm in the habit of writing object here. So this means that this class inherits from the object class. I'll explain more about inheritance later, but the idea is just that the rational class is going to share some things in common with the object class, and we would like access to all the attributes and methods of the object class as we define the rational class. Then, within the class definition, we have our methods defined. And we mentioned methods are functions that belong to a particular object or class. So here, we have a function definition. And we're defining the init method. This is a special method in Python. Python looks for this method whenever we create a new object of a particular class. So whenever we create a rational object, Python's going to look for the rational init method. The init method will take 3 arguments. Self, which is a special argument that I'll describe in a moment, numerator, and denominator, both of which are self-explanatory. And then in the init method, all we're going to do is create some attributes and initialize them, or assign values to them. Self, the argument self, refers to this object itself. When we create a new object of the rational class, that object is going to be automatically passed in to the init method as the first argument. And whenever we call a method of an object, that object becomes the first argument of the method. For example, when I have a list and I call the append method, if I take mylist.append and I do, whoops, let's see here. I could also write this as list, like the class, dot append, my list, and then the object that I want to append. And we see the letter C got appended to the list. So when I call mylist.append, my list automatically gets plopped in, sent in to the append method as the first argument. So the object itself will always be the first argument of the method of any object. And we want to create a new attribute of this object, of self. Just like earlier, we accessed the real attribute of a complex number. We could also do that for a integer. So here we have the real attribute of an integer. We're going to create a numerator using the same dot attribute syntax. We're going to create a numerator for this object. And it's going to be equal to the numerator that got passed in when we created the object. We're going to do the same for denominator. So let's go ahead and define this class. And we can construct a new rational by calling rational and supplying that numerator and denominator. Remember, self is automatically supplied. It's automatically passed in as the first argument. So here we have our fraction 4/3, numerator 4, denominator 3. I could even ask what is the numerator of our fraction, and we see that it's 4. So in this init method, we're initializing these attributes to be equal to the arguments that were passed in at object creation. When we printed out the fraction, we got this very nice 4/3. And that was taken care of by this repr method. Repr defines the representation of an object. And here I have the repr method return a string where we insert the numerator and the denominator on either side of a slash. So here's how we defined how this object would be printed out. Let's imagine for a moment that we had not included this repr method. So then we could make a rational object, and if we tried to print out that rational object, we would get this main rational object at this address in memory. And this is not very informative. This tells us almost nothing about what is going on with this object. This doesn't mean that the object is in any way different. We'll call this frac no repr. I can still access the numerator and the denominator, but there's no simple or meaningful representation of this object that I can print out. So I need, whenever I'm defining a new class, a new type of object, at a bare minimum, I'll want to provide the instructions for initializing a new object of that class, the init method, as well as a definition for how this object should be represented to the user. That's what I'm doing here. I'm specifying how should I represent this object when a user interacts with it. And this kind of comes back, you may remember when we were talking about sets, I mentioned that the set prints out in a particular order, but that does not mean the set is in that order. The set is unordered. But in order for you and I to have an understanding of what's inside the set, Python needs some kind of way to represent the set visually to us. It doesn't mean that's accurate to how the elements are arranged in memory. It just means that a set has a particular representation in text, given by its repr method. So there's some text here talking a little bit more about that first argument self, which I've already explained a bit, and giving another example of what happens when we call the method of an object. So here we have a myClass class. It's very simple. The initialization takes self, as it always will, as well as some number, and we create an attribute for this object, self.num equal to num. And then we have a method, which also takes self as an argument, and all this method does is print out the num attribute of the object. We can create a myClass object, and then we can call myClass.doIt. And what happens when we call that is it prints out the number, just as we would expect. Notice we didn't supply any arguments to do it. MyClass, the object, was automatically passed in as the first argument, as self. We could call doIt from the class directly. Here we have capitalized myClass. This is the class. This is an object. This is the class. And we call the doIt method from the class, but then we have to supply a particular object for self. So when we call myClass.doIt, self is understood because myClass, the object itself, is automatically passed in as the first argument. This is calling this argument self, the first argument of a method, is so common. This is such a strong convention that you will never see something else here. We could name self anything else. It's totally arbitrary. We could choose this or Apple or Wizard, but you will always see self here. Pretty much no one ever puts anything different. And conventions are useful. Conventions help aid clarity. They make your code more readable. They are built based on or they mean your code conforms to the expectations others will have, so they'll have an easier time understanding your code. The other thing you might have noticed was these methods are surrounded by double underscores on either side. So we have 1, 2 underscores on either side of the method. Double underscores. So these are sometimes called dunder for double under methods. Double underscore methods. Dunder methods. So you may encounter this term dunder methods. The dunder methods of a class or object are the points at which that class hooks into fundamental elements of Python. So things like class initialization, object initialization, object representation. So repr here is automatically called when we actually even just evaluate. Oh, not when we evaluate. Sorry, whenever we print. Actually, it's because I haven't run this. That's the problem. So repr is called actually anytime we evaluate that object and it needs to be returned with some visual representation. Python automatically calls this repr method. And generally, those double underscore methods will be relied upon by other parts of the Python language. Python expects these dunder methods to be defined. Now, it's okay if you don't define one. It won't break anything. Instead, we will simply fall back onto the dunder methods of whatever class our class inherits from. Again, we'll talk more about inheritance later. Dunder methods are typically not intended to be called directly. We never call dunder methods from the object, but they hook into Python in special ways and are called by Python when we do specific things with the object within Python. In general, we often use underscores to denote variables or functions that we don't expect the user to use directly, but instead intend for use by other parts of our code that a user may interact with. So let's see an example of that by filling out some functionality in our rational class. So thus far, our rational object is very simple. It can't do very much. We can initialize it and we can print it out, but we can't do anything with it. We can't do simple arithmetic with it. We can't even reduce it to its simplest representation. For example, if I have 15 thirds, this prints out as 15 thirds. It doesn't get reduced to 5. And likewise, if I have 3/15ths, this doesn't get, sorry, I keep writing with a slash there. This doesn't get reduced to 1/5. It remains 3/15ths. So let's write some methods that will allow us to simplify our fractions. So we have the init and repr methods we had before, but we're going to define 2 new methods. We're going to define a reduce method, which will perform the actual simplification of our fraction. And in order to do that, we'll need to compute the greatest common divisor of our numerator and denominator. So we'll also define a GCD for greatest common divisor method. And we don't intend for someone working with a rational number to call this great GCD method on its own, because that's probably not information that our user needs. Probably our user just wants to simplify the fraction. So we're going to call this underscore GCD to indicate that this is a helper method, not intended to be called directly, but for helping us in another method. So here, most of this, is not very difficult mathematics. GCD, we find the smaller number between the numerator and the denominator. We compute all the divisors of that smaller number, each number up to the number itself, including the number itself, as long as that smaller number is evenly divided by the potential divisor. Then we look at the max, the larger number, and we find which divisors of the smaller number also divide the larger number. So for each divisor in small divisors, we check if the larger number is evenly divided by that smaller divisor. And then we print out the max of that set of common divisors. So that'll give us the greatest common divisor. So once we have this greatest common divisor, we can simply update the numerator and denominator by dividing them both by their greatest common divisor. And notice here we're mutating the object, we're changing its attributes. So as I mentioned earlier, we'll often manipulate an object's attributes via its methods. So here we're doing that. We're mutating the object, changing its numerator and denominator via its methods. And then finally, we return the object itself. So we can see how this works. So we create a fraction, 16/32. We reduce it, and when we print it out now, we see 1/2, 16/32. So this is an example of a bit more fleshed out class definition that has some functionality with a method that in other languages we might call this a public method, and we would call this a private method. Python has no distinction between public and private methods. There is no such thing as a private method or a public method. They are all public methods. However, the idea of a method being private or not intended for direct use, of course, still applies. So rather than forbidding a Python programmer from accessing certain methods of an object, we instead simply signal to the programmer using an underscore that this is a helper method and is not intended for direct use. So that lets the programmer know this should be treated like a private method. It's possible to use it as a public method, but it's intended to be treated like a private method. I'm going to conclude this lecture here, and then we'll carry on fleshing out this rational number and adding some functionality until we create an object that we can actually do math with.